Well, all right then. Some things to look forward to.
I love it. It might be a little too much to say.
It's
I don't think it's that exciting.
just something.
Yes, it's something.
All right then. Let's move into another chapter, shall we?
Yeah.
We shall. Chapter 8. We're just moving along here, but we're going to start walking down again because these are going to be heavy topics, as it were. But it's good stuff. So, actually, I think what I will do is I'm going to first give you the Astronomy 111 version as a big picture, and then we'll say, and now let's get bogged down in the details. Let's put in the math.
You should.
What's that?
Everything's fun, and then you add math.
And then you had
I was going to say, for Astronomy 111, you should start with the...
Yeah. Let's start with the 310 version.
Just to make sure you're
And if there's anybody left, yeah.
Just if you had any questions about your TAs and whether or not they know enough about the subject, let's
It's
start
just-
with what they had to learn and go back to what we are going to learn.
Exactly, yes. Alrighty then. Well, I did in fact kind of post the Astronomy 110 version of slides here. So, but I think it is useful to kind of go first through the kind of the big picture, and then we'll talk about, okay, now the fun part, now the math, or something. Yeah. So, I had notes from Keith to this presentation. I have no idea what you're talking about, and I don't want to try it.
People's always trying to get you to other things.
I know, that's right. And I said, well, sometimes it's helpful.
Get paid.
And I have pretty much moved to the cloud, as it were, using slides instead of PowerPoint and all that, because I don't typically need all the crap that PowerPoint can give you, I don't need it to bounce and introduce itself when I have every line coming in.
The only time I've used like dynamic intros to slides was when I did things for like 5th grade.
Yeah, right. It's like, okay, let's make it more about looks than about content can be what happens there. Yeah, right. Yeah, boing, boing, boing. Yeah.
What I do this is like in Microsoft Office when they have the little paperclip guy, says, do you need assistance? I miss that.
This is great. This is your writing brain science.
Yeah.
It looks like you're trying to solve this algorithm. Do you need help? It's a yes.
And that's just good at all times. It's like, oh my God. Yeah. Well, all right.
Good job. We killed it.
That's right. Thanks a lot. Oh, I have so much less work all of a sudden. All right then. So stellar spectra. So we know, and we're going to be more, much more detail about this down the road. But again, big picture, you can think of stellar spectra, the absorption lines in a stellar spectrum, like in the sun spectrum, to be caused by cooler layer of outer atmosphere that is absorbing light at specific wavelengths coming up from the hotter, denser layers below. So the hotter, denser layers below are a source of continuous spectrum, rainbow continuum, but the cooler gas above it absorbs some wavelengths out and removes them from the beam of light heading our way, and so as a result there's light missing at those wavelengths, namely spectral line wavelengths where electrons can jump up in atoms to higher energy levels after absorbing those photons. And because they don't always re-emit the same wavelength in the same direction that it came from, in other words, when they make a downward transition, they spit out a photon in some random direction, and or you might have a single upwards transition followed by several downwards transitions, so you're not replacing the photon from that standpoint either. As a result, you get an absorption line spectrum. And so that's what is being shown here. Sunlight leaving the stars absorbed by atoms or molecules in the star's atmosphere. Only for the coolest stars are there any molecules. The sun doesn't have any molecules at all. It's too hot for that. But the coolest stars, titanium oxide is a pretty stable molecule. And so it's able to exist at a temperature of around 3,000 Kelvin. So the coolest stars have some molecules showing up in their spectrum. but warmer stars like the sun. But in any way, so a continuous Planck spectrum emerges from the hot interior of the star. As radiation passes through the star's atmosphere, atoms absorb photons of certain wavelengths, causing absorption lines in the stellar spectrum. Atoms in the hot outer atmosphere of the star may also emit photons, causing emission lines in the spectrum of some stars. There are the exceptions, but some stars do have emission lines in their spectrum. Okay, any questions so far? All right. So this makes the absorption lines in the spectrum. Sometimes when they see emission lines, I just read all that, since I said that again, superimposed on an underlying Planck or continuous spectrum. Big words to explain the small words, or to state the small words that nobody can read in the back of the room or on the video. So, okay, so I just restated that. It used to be that computers were made of flesh and blood. The word computer was literally used for people whose job was to compute things. My lovely wife almost became a computer for Subramanian Chandrasekhar back when she was in graduate school, because the famous Chandrasekhar wanted somebody to do calculations for him, go through the details of the calculations. He'd set the big picture and then say, here, smart student, go through and do these calculations and figure out where it all leads. In other words, the former word for mathematica was graduate student, so to speak, or computer. Only later did computer come to mean mechanical computation devices. So Edward Pickering in the late 1800s was an astronomer at Harvard who hired a bunch of computers, namely women who would basically do things like analyzing spectra, doing the details of looking over and classifying spectra and so forth for him. So the thing is that these are women who, by all rights, could have been, professional astronomers with professorships and so forth in and of themselves. So the bad news is, in the 1880s, 1890s, society wasn't as far along as it is today, and so capable women were not given the opportunity to become professors of astronomy. The good news is Pickering and others hired such women to do detailed work in astronomy on his behalf. And they are now recognized for the very fundamental discoveries that they made. And so here is a group of such women in 1890, many of whom are now famous for discoveries that they made, and in particular for the classification of stellar spectra. The modern classification scheme for stellar spectra goes OBAF GKM, and there is a well-known mnemonic for that. So OBAF GKM. Yes, we sing the tune. OBAF GKM is really a silly thing to sing or something. Anyway, as we'll see, it's actually a temperature sequence. It's based on the strengths of spectral lines. Anybody know what the acronym is to remember OBAF GKM? Yeah, O be a fine girl, kiss me. Or O be a fine guy, kiss me. Whatever you prefer. You could even say Birkin if you like pickles or something. I don't know, but in any case. So yeah, that's the classic O be a fine guy, girl, kiss me. I learned this before I knew there was an acronym when I was an amateur astronomer kid. And so the way I still remember it to this day is to take advantage of the fact that it is in fact kind of pronounceable. I just say OBAF Gookum to myself to remember it. And I find that many students say, yeah, why not OBAF Gookum? So maybe you too can just be an OBAF Gookum like me, so to speak. So initially, the classification scheme was based on the strengths of the hydrogen lines. In other words, how dark are the hydrogen absorption lines in the spectrum? And the initial sequence went A, B, C, D, E, F, G, and so on and so forth. Yes, but do I have her in here? Somewhere I have her in here. Oh, what? No, there's Cecilia Payne-Gaposchkin, you know, she was awesome. Annie Jump Cannon, what an awesome name is that, huh? Annie Jump Cannon.
Annie Jump Canyon.
Just Cannon. Okay. Annie Jump Cannon. I mean, how awesome is it to have your middle name be Jump, right? Annie Jump Cannon classified several 100,000 stellar spectra. She got to the point where she could do like 1 every 20 seconds or something like that, which if you've ever tried, probably haven't, if you've ever tried to classify stellar spectra, you would not be doing 1 every 20 seconds. It's like, well, how strong is this line compared to these 2 other spectra? But she just got so good at it, she just could like just whip through these things in relative terms. And she arranged, she eliminated, basically she said, okay, well there's more than just hydrogen. So let me look at other spectral lines too. And she tossed a lot of the original letters and kept the ones that are in the current sequence, O, B, A, F, G, K, M. And so the modern sequence is based not only on the strengths of hydrogen lines, but other lines as well. And with that, it's a nice continuous sequence. There's systematic ways in which the strengths of all the different types of spectral lines vary as you go from O through M. And it turns out, as we'll see, that it's really a temperature sequence. Initially, astronomers thought that stars with stronger hydrogen lines must have more hydrogen. But then, as we'll see later on, Cecilia Payne-Gaposchkin, in her 1925 PhD thesis, she was Cecilia Payne at the time, but she decided her name was not quite cool enough, so she married Sergei Gaposchkin, so she could be Cecilia Payne-Gaposchkin. Oh, she wasn't trying to make her name cool, she actually liked the guy. But anyway, he was a fellow astronomer too. In her PhD thesis, she showed that the variations in the strengths of hydrogen lines and other spectral lines was actually due to temperature differences, not due to abundance differences. And that all normal stars are made almost entirely of hydrogen and helium. That's a pretty good accomplishment to be a graduate student, and for your PhD, you show that most of the ordinary matter in the universe, at the time it was thought most matter, they didn't know about dark matter at that point. Most of the matter in the universe is in the form of hydrogen and helium. So it's often considered to be the greatest PhD thesis ever written in astronomy, because what a fundamental discovery to be made in a PhD thesis. Yes, questions?
It's impressive.
It is impressive, as a matter of fact. Yes, I mean, I'd like to have something like that to my name, you know. I discovered what most of the universe is made of. Thank you very much. Any questions? Right? So, go ahead.
Any questions? What's the universe?
And what's the universe? Next.
But were you there?
I'm here. Right? I'm here. So, I'm not there, but I'm here.
People like sitting in their graves.
Wherever you are, wherever you go, there you are, right? Anyway, the spectral classes were further subdivided with numbers. So numbers that go from 0 through 9. And so, for example, for A stars, there's A0, A1, A2, blah, 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 A9, and then next would come F0, F1, blah, 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 F9, G0, etc., etc. So there's also subdivisions. Each letter class is subdivided into 10 subclasses that are numbered like that. Of course, the cutoffs are kind of arbitrary, right? You know, this is a human scheme. But there really is a systematic variation. And I believe it starts with O5, just because with O they didn't find that there was a reason to make 10 subdivisions. So it's, if I recall correctly, it starts with O5 and they go through O9. and then B0, B1, and so on and so forth. So here's some examples of various spectra of different classes. And what defines spectral class A0 is that they have the strongest hydrogen lines. So this is the H alpha line right here. This is H alpha. Do you remember what H alpha is? Which spectral line that is? What transition it corresponds to? These are beta. So we use we use L alpha, L beta, and so forth for the Lyman series. So H alpha is the lowest energy, longest wavelength transition in the Balmer series. And you remember what levels are involved in the Balmer series? Quick, before I get to the slide. 2. Yeah, it starts or ends on n equals 2. So the Balmer series starts or ends on n equals 2. So Balmer alpha, H alpha, is the n equals 3 to n equals 2 transition, and it's red. N equals 4 to 2 is H beta, and it's a lovely turquoise, lovely turquoise. And then 5 to 2, 3, 4, 5 to 2, and 6 to 2, those are kind of an indigo color, right? Yeah, kind of indigo, maybe bluish purple, you know, and if you just want to be annoying, you could call it indigo. Anyway. Yeah, it's indigo-ish purple, right? And it's like, die! Right? Yeah. So you really get me, right? That indigo-ish purple, it's bluish indigo.
So it's indigo-ish indigo.
Right, indigo-ish indigo, right. It's not quite indigo, but it's an indigo-ish indigo. Yeah. Indigo. So anyway, A0 has the strongest hydrogen line. So here's H alpha, here's H beta, which is not really that blue color it's shown in this picture. It's really more turquoise color, but whatever. And so on. So notice that the hydrogen lines, they're darkest, easiest to notice at A0, and they become systematically weaker on either side of that. And other lines kick in and are stronger for other spectral types. So there are, in fact, okay, here. Let's repeat then. Stars are classified according to the appearance of their spectra. Absorption line strengths depend mainly on the temperature, and we'll see why that is. Full sequences: Obaf Cookham, Oviafine Girl Kiss Me, Oviafine Guy Kiss Me. The Sun is of spectral type G2. The Sun is a G2 star. And in fact, it's a main sequence star to which we attach we indicate that with a Roman numeral 5. So the star's the Sun spectral class is G2 Roman numeral 5. That's the Sun in a nutshell. That's its spectral class.
What's the Roman numeral?
We'll see that those are what are called luminosity classes. So main sequence stars are Roman numeral 5, and then there's subgiants, giants, supergiants, and yeah. Right. So there's all these different luminosity classes, and we'll talk about that too. So the hottest stars have weak absorption by hydrogen and helium. Those are type O. In the middle, strong hydrogen absorption, type A. These are like general trends. And then the coolest stars have absorption by heavy elements. So to an astronomer, a heavy element has the following definition. Is it hydrogen? No. Is it helium? No. Then it's a heavy element. If it ain't hydrogen, it ain't helium, it's a heavy element. You may know that we have another name for that, which is much dumber than heavy element, which is metal. Yeah. So at one point, I think it was B who put like the periodic table for astronomers. And basically, it's X, Y, Z, because as we'll see too, capital X is used to represent the hydrogen abundance in the star, capital Y is used to represent the helium abundance, and Z is the abundance of everything else, which we call metals. Carbon is a metal to an astronomer. Nitrogen is a metal to an astronomer. We make no sense whatsoever to other scientists, but who cares? Because we're studying the universe as a whole, and they're just studying your little parts of it. So we're better than them anyway. Quote me on that. And if somebody wouldn't believe that I would say something like that, point him to the video. So anyway, Diego can verify this. That's right. Absorption by heavy elements or molecules in the coolest stars like Type M here. Notice the Type M stars, they really get more and more blanketed by absorption lines. And in particular, a lot of that is because remember that molecules can vibrate as well as have electronic transitions. They have vibrational transitions that can absorb whole bands of wavelengths. And so the coolest stars get very smudgy looking spectra, so to speak. So what experts do, how you can actually classify stars, is you can get these atlases of standard stellar spectra. And it used to be done photographically, now you can do it on a computer, where you could say, you look at the star and the star spectrum, and you look at various spectral lines, and you try to find two spectra that they're between, so to speak. In other words, this set of spectral lines is stronger than in this star, but weaker than in this star, and this star is G4, and this star is G6, so the star I'm classifying is G5. You kind of do that sort of thing to figure out what the spectral class is. So again, Annie Jumpcannon got to the point where she could just look at the spectral lines and say, that looks like about a G4, and then verify it, you know. So she did several hundred thousand, so I guess she probably was like seeing spectra in her sleep by that point.
She became a spectrum.
What's that?
She became a spectrum.
She became a spectrum, that's right.
That's why we gave you a 3 exam.
That's right, yes, exactly. So here's the dependence of spectral line strengths on temperature. So line strength, as we'll see, what that really means is what's called the equivalent width, or in other words, how wide would a spectral line have to be if it had 100% absorption in the part where absorption is happening for that spectral line. How wide in wavelength would it have to be removing the same amount of light from the spectrum as the actual spectral line, which does not ever completely remove light. No absorption line is really black, it's just that there's less light in the absorption line than there is in other wavelengths. So we have what's called the equivalent width, meaning, well, what if you had a completely black spectral line? How wide would it have to be to represent the same amount of light being lost as the actual spectral line does? So these are really, it says line strength, what they're really talking about is equivalent widths. And these are plots versus spectral type. For example, for hydrogen, you can see it peaks up at A0. Calcium, Roman numeral 2, peaks around K0, which means that the sun, for example, at G2, has pretty strong calcium 2 lines. G stars like the sun have pretty strong calcium 2 lines. What is calcium 2, you say? I've got that zoomed in on the screen, but whatever. Just listen, you'll get it. It's fine. Quit complaining back there. So, astronomers have this also funny notation where, while a chemist, silly people that they are, sorry, there we go, found the right one there. I'll just point it.
But
I got tired of listening to your griping, so I'm just going to repoint it. Jeez, some people.
there's nothing that can't be accomplished with the right hand negative.
That's right. That's pretty much true. So to a chemist, if I had, say, calcium that had 1 electron removed from it, a chemist calls that Ca+. And calcium that has 2 electrons removed from it is Ca++. And you know, if eventually you just start writing like 3+, 4+, 5+, you know, like the number 5 and plus or whatever. This isn't how astronomers do it. Instead, astronomers call Ca plus Ca Roman numeral 2. And they call Ca plus plus Ca Roman numeral 3. In other words, you use a Roman numeral, which is one more than the number of electrons that has been removed from the atom, because we want neutral calcium to be Ca Roman numeral 1. Because that's why.
I think there's just like this fixed setup of like all scientists and then astronomers come in and just like, nah.
Pretty much, yeah. We've got these weird traditions in astronomy. And I'm just, you know, you just get used to it. It's just the way it is. So Ca2 is single ionized calcium. Ca1 is neutral calcium. And so you can see Ca1 has a different curve than Ca1 lines have a different curve than Ca2 lines. And on. So Fe2 would be singly ionized iron, Fe1 is neutral iron, and so on and so forth. So you can see there's systematic variations for every imaginable spectral line in its strength as a function of spectral type. And ultimately that's because spectral types are kind of a code for temperature, with O being the hottest and M being the coolest. And so for any given type of spectral line, there's kind of a Goldilocks temperature where the temperature is just right to maximize how strong those lines are in the star spectrum. And if you're hotter or cooler than that, then the lines are not as strong as at the Goldilocks temperature, so to speak. Okay, any questions? Yes?
In like basic astronomy, when we were talking, we said that specific energy the only thing absorbed or given off was specific energies by the electrons going up and down orbitals.
Yep.
So why can these elements be absorbed like over like a range, like a piece?
So the thing is, so note that what we're talking about here on the x-axis is spectral type, not wavelength. So this is, or equivalently, this is temperature. So in other words, the calcium-2 line is always at the same, a given calcium-2 line, this is actually the whole set of calcium-2 lines, pick any one of them. That line is at a fixed wavelength, right? But how dark is that line is what changes as a function of temperature. That's what this is applied. It's how dark is the spectral line. So in our other graphic, back to like this one right here, here's the H alpha line. It's always this red wavelength, but it becomes darker for A0 than it is at other. So you can think of those plots as plot darkness versus spectral type coming out of the page in that direction, and that's what that plot is
Then,
showing.
actually the other one, how come the other, the same element is on different wavelengths then? Because there's iron 1 on 2 different wavelengths.
So iron, neutral iron, and so Fe1 is neutral iron, Fe2 is singly ionized iron. They have a completely different spectrum from one another. That's the thing. Because you remove that electron, and that changes the energy levels of all the electrons in the atom, because they're no longer interacting with that missing electron anymore, and because the nucleus can be seen better by the other electrons when you remove an electron.
What I mean is it's the same element on 2 different wavelengths.
Do you mean like why are there 2 different plots here? Like
on the other.
On the other.
They'll have it across the bottom. They'll say Fe1 twice.
Okay. Oh, I see what you mean. Yeah, I gotcha. I see what you mean. Yeah. So why is there Fe1, and so forth? The idea there is they're not unlike for hydrogen and helium, unlike for hydrogen here where they're bothering to say, here's the H alpha spectral line, here's the H beta spectral line. They're not labeling the different spectral lines for other ones. So just like hydrogen has a whole slew of spectral lines, every species has a whole slew of spectral lines, and they're they're not bothering to say this is Fe1 beta, this is Fe or anything like that. It's just, this would be, to the full thing, you should say something like Fe1 427 for 427 nanometers or whatever. That wavelength of Fe1. That's how we generally do it. So it's like Fe1 and then a number which specifies the wavelength. So there's a whole slew of wavelengths of spectral lines that are all Fe1 spectral lines, Fe2 spectral lines, and so forth. And they vary together. In other words, all the spectral lines of neutral iron vary in strength together. When one is strong, the other ones become stronger as well. Because it's a combination of, basically the strengths of the spectral lines are set by a combination of how abundant is the element and what's the temperature. And the temperature is what controls the variation of strength relative to, for different stars relative to one another. But there is some factor of abundance in there as well. But the thing is that initially, astronomers made the natural assumption that the fact that hydrogen lines were stronger in A0 stars and weak in a star like the Sun, astronomers initially assumed that that meant that A0 stars had a lot more hydrogen in them than the Sun does. But that turns out not to be the case. Almost all of the variation in line strength for hydrogen is due to temperature, not due to abundance. So here's a reminder again of the hydrogen energy level diagram, and in particular, the visible spectral lines are the Balmer series lines that start or end on n=2, because the Lyman series lines are in the, not the visible, but the ultraviolet because of the much larger energies. And the Hodgkin series are not in the visible, but the infrared, right, yeah. So we tend to look at visible light spectra, so the Balmer series lines are the ones that we typically think of as the hydrogen spectral lines when we're talking about spectral lines in star spectra. And relevant here, in particular, is only hydrogen atoms with the electron in the n=2 orbital can produce hydrogen, visible hydrogen absorption lines, Balmer series absorption lines. You have to start with n=2 and absorb a photon to jump to n=3 or 4 or 5 or 6 or whatever. So you got to be in n=2 in the first place. So here's Cecilia Payne-Gaposchkin, who, again, at the time she did this, was Cecilia Payne, who was the person to show that what I said is true, that it's a temperature sequence, not an abundance sequence when it comes to the strengths of the hydrogen lines. And the way she did that was to use the newly discovered / invented equation from Bose about which relates the abundances of, Bose and Boltzmann, which relates abundances of different species in a star's atmosphere, different ionization species in a star's atmosphere. So we have what we can call kind of like the Balmer thermometer. So this is the qualitative in words description that we're going to add math to, okay? The idea is this, that, so first of all, A0 stars, which have the strong spectral lines, and actually I think I might be, not, I think it's A0, it might be A1, but I think it is A0 where the lines are strongest. But in any case, it's at a temperature that's approximately 10,000 Kelvin. It's not quite 10,000 Kelvin, it's 9,000 something Kelvin where the hydrogen lines are the strongest. So we're just going to call it about 10,000 Kelvin here where the hydrogen lines are strongest. Here's the deal. If the temperature is much less than 10,000 Kelvin, then collisions, how do I want to say this? We need, in order to get strong hydrogen lines, we need to have as many hydrogen atoms with electrons in the n=2 level as possible, because those are the ones that can make the hydrogen lines, okay? But if you leave a hydrogen atom to its own devices and don't interact with it, where's the electron going to be? In the ground state, right? They want to be in the ground state, so to speak. How can you get electrons to n equals 2? Well, we know one way would be to have a Lyman alpha photon come in and kick it from the ground state up to n equals 2. That's one way, but more common in the stellar atmosphere is just collisions. If a hydrogen atom in the ground state collides with anything else, an electron, another hydrogen atom, a helium atom, whatever, some of the kinetic energy of the collision can excite the electron to the n equals 2 level. And then the kinetic energy afterwards is smaller because some of it was used to promote the electron to the n equals 2 level. So it's not just photons that can promote electrons to higher energy levels, collisions can do it too. And that's more forgiving in that it turns out that the collision doesn't have to have exactly the energy necessary to promote the electron to the next level. Unlike a photon, which has to have very precise energy, as long as the collision has more than enough energy, there's more than enough kinetic energy available, you can promote the electron to a higher energy level, and then that's just, afterwards there's less kinetic energy after the collision because of the energy that went into promoting the electron. So the idea is, Goldilocks wanted a star with nice strong hydrogen lines. And first she went to a star that was too cool. And that meant that because the atoms were not moving fast enough, because it was well less than 10,000 Kelvin, very few hydrogen atoms had their electrons in the n equals 2 level. They were almost all in the ground state because the collisions aren't energetic enough to promote a significant number of them up into the n equals 2 level. And then she went to a star that was too hot. In a very hot star, the collisions are so violent that they simply strip the electrons off of most of the hydrogen atoms. They ionize them. You can't get any spectral lines from bare protons because there's no electron available to make energy transitions. So you can't absorb anything with any specific wavelengths if you've got a bare proton. So that star was too hot. Almost all of the hydrogen was ionized in that star. But then she found a star around 10,000 Kelvin surface temperature, which was just right in that there was the optimum, if you will, the largest possible number of hydrogen atoms that had the electrons sitting in n equals 2 without it being so hot that the electrons were being stripped off altogether. So you get the strongest hydrogen lines in a temperature around 10,000 Kelvin because a significant number of hydrogen atoms remain neutral but are also excited to the n equals 2 level, able to form Balmer absorption lines. As we'll see, it's still a really tiny fraction. You never get more than a very small fraction in n equals 2, but the fraction is largest at around 10,000 Kelvin, and so you get the strongest hydrogen lines in the visible spectrum, the strongest Balmer lines at a temperature of around 10,000 Kelvin. Okay? And then the idea is the same kind of argument can be made for the spectral lines of other species, but the temperature that optimizes it is different for other species. And we'll go through an example of that with ionized calcium to show why ionized calcium is strong in cooler stars like the sun, whereas hydrogen is strong in hotter stars, A-stars. Okay, any questions? So that was the Astronomy 111 version. Now it's time for the math. Woo! No, it's not time for the break. Yes, well, that clock is slow. There's still like 7 or 8 glorious minutes before the break. You tried. You tried.
Find a tangent.
Yeah, find a tangent. Get him started on something.
So creationists.
What?
I said so creationists.
So creationists.
So creationist walks into a bar. That's the joke.
That's the joke. Creationist walks into a bar. Yeah, actually, joke I heard one song, Prairie Home Companion. It's working. Prairie Home Companion. Garrison Keillor, I think he's an Episcopalian. So So he had a joke, they had a joke show every year where they just tell joke after joke after joke. So he decided to rib his fellow Christians who are Baptists with the following bit of humor. Why do you always invite 2 Baptists to go with you on your fishing trip? Because if you invite 1 Baptist, he'll drink all your alcohol. But if you invite 2 Baptists, they won't drink any. It's actually a pretty good joke. All right.
Oh, pretenses. Quick, 5 minutes ago.
The Boltzmann equation. So, oh, by the way, of course, we've said the story about the star that walks into the bar, right?
Nope.
What? No, we have to. The dead the creationist walks into the bar. Okay, star walks into a bar, says, I'm the brightest star in the sky. Bartender says,
Are you serious?
are you serious? Yeah. Uh-huh. So, a furry animal walks into a bar, grabs a sandwich, orders a sandwich, eats the sandwich, and then pulls out a gun and just shoots the place up, totally shoots the place up. Bartender says, what the hell? Why did you do that? So the furry creature hands him a card, I said, the small furry, I've got to be ready to tell these things. The furry creature says to the bartender, I'm a koala, look me up. And so then the guy looks up koala and it says, eats, shoots, and leaves. Oh, oh, oh.
Oh dear.
So, the Boltzmann equation is what we'll talk about here. How many precious minutes do we still have? Thank God, it's on the video. Anyway.
We're making that practice.
When we were
Describes the relative populations of atoms of a given species in its various energy levels. So, like for example, for hydrogen, how many of them are in the ground state? How many of them are in n equals 2? How many of them are in n equals 3? And so forth. H for hydrogen tells us how many have the electron in n equals 1 versus n equals 2 versus n equals 3, etc. What fraction of the hydrogen atoms are in the ground state, and the first excited state, and second excited state, and so forth. So what we're going to do may not just be hydrogen, so we'll be generic here. Let S sub A and S sub B be the sets of quantum numbers specifying 2 quantum states of an atom. consider hydrogen, a neutral hydrogen atom. SA and SB could be two sets of values so what was the set of quantum numbers that specifies a hydrogen state? We had N was one of them, right? What were the other ones? And then we make our tree diagrams. L, yeah. And then two M's. M sub L, right? Where M sub L goes from minus L to L in steps of 1, right? And then the other one is M sub S, right? Which can be plus or minus a half. Right? So remember that those four numbers tell us the state of the hydrogen atom. So we could be saying one of the states is N equals 1, L equals 0, M sub L equals 0, M sub S is plus 1/2. And another one of this, the other state could be N equals 3, L equals 1, M sub L equals 1, M sub S equals minus 1/2. Just two of those sets of quantum numbers. Ah, break time.
Video.
Video time.
Can we look up something on YouTube?
Sure. Go for it. Should this be on that?
I'm the person that's always copying.
I'm the person that actually.
Okay, it's this video again.